afternoon, everyone. I'm George Findikakis, and our next panel is about nuclear energy and the SMRs, the small modular reactors. Lately we've been hearing a lot about this concept, this new technology. Some say, there are two blocks actually, two perspectives. Many say the SMRs are the future of nuclear power generation, others not. And of course the $1 million question is, can these small reactors make nuclear power cost efficient? I welcome our distinguished guests with whom we will explore all these topics within the next 1 hour. Dr. Michael Drury, Managing Director of Lucid Catalyst with a distinguished career in the nuclear industry. Professor Ionat Pourika, Executive Director at the Advisory Center for Energy and Environment of the Romanian Academy, who is with us online. And Dr. Dionysios Chionis, co-founder of Atlos Energy. Dr. Drury, the floor is yours.
Well, firstly, thank you for inviting me. It's a pleasure to come to Athens, and it's my first time here, so it's really good to kind of have a run around this morning and see the sights, but it's a pleasure to kind of present to those that have stayed on to the end of the day. I'm going to try and go through this as fast as I can so we can have a little bit more time to kind of talk a bit later, but hopefully you'll get a copy of all of these slides, so don't worry about trying to read it. More, it's about the imagery and the messages that you get from these. So if you look at the global energy projection to 2050, there's a huge demand that's coming, and we need to be prepared and ready to supply the energy for that demand. And it's not just in your typical electricity production, 17%, 18% of global emissions comes from a small proportion, but 82% comes from industry. That's a huge proportion that we have to find a way to decarbonise, and there's opportunities to address that with nuclear. But if you're going to provide nuclear, you have to think about, well, how do you support that? It's not just in electrification. Yeah, that'll work, and there's great opportunities for that, but actually there's a lot of opportunity in if you can supply the heat direct to some of those industrial applications. But there's also a huge section of energy demand that's just for transport. So how do we decarbonise those transport industries? Now, a lot of people say, we just use hydrogen, it's fine. Yeah, you can, absolutely. But how are you going to make that hydrogen? And how are you going to make it cost effective? Because the challenge isn't necessarily what tech can you use, it's what tech can you use that's actually competitive with today's energy price. How do you do that? Now, you have to compare those energies and what can be used for an SMR, and not everything can be done by nuclear on those industrial applications. Some of those heats are actually way above the temperature that the reactors can work at. So we have lots and lots of different reactor types. In fact, if you look at the kind of reactors that are kind of being designed today, that's not to look at the reports that will show 300 to 400 different reactor variations and vendors, but actually those that are kind of in projects or announced or going through designs, whether those be paper designs, whether those be physical metal that you can see, but actually they're just test pieces, or whether those be reactors that are kind of consistent with today's technology, light water reactors that are all around the world, but they're being made in a slightly smaller way. Why are they doing it smaller? Well, it goes back to the need for getting the cost of that energy down. And to get that cost of energy down, some of those reactors are looking at different technologies, Generation 4 technologies. And to be honest, they're not Generation 4 technologies, they're Generation 1 technologies, because they were all developed at the same time, and these just happen to be called the next generation. For me, I think Generation 4 represents something slightly different. They're looking more towards passive safety control measures. They're looking more towards heat generation, and they're also small and modular in their construction approach. Is that enough to compete? Is it enough to say, well, can we get our prices as low as $20 per megawatt hour? It's a real challenge. And if we supply these nuclear reactors, how do we meet those new customers? Let's just take one example, right? Data centers. We talked about it a little bit earlier. 465 terawatt hours, I think it was, that was presented on the screen, with 1,000 in 2026. You know, the time it took to get to 465 terawatt hours was around about 30 years. You're moving from 22 to 26, according to the chart that was on there, in 4 years. That energy growth is exponential. But it's not just about the energy, it's also about, well, hold on, if I build these data centers, and it's not just one company, you know, it's not just 2 companies, it's not just 3 companies, it's loads of these companies are moving data centers forward. And when they do that, they're not just building a 5 gigawatt data center. Great, yes, I'm going to have a hyperscale facility. No, what they're doing is they're building bit by bit, growing that data center, and eventually it becomes a 5 gigawatt data center. So do you deploy a large 5 gigawatt nuclear reactor? No, you're going to have to find a way to meet that demand as it grows. How do you make the modularization for everything on that power station? So now you have to look at not just the energy, the kettle, but also the power station, the balance of plant. And how do you get that to scale up and grow as the technologies move? Because if you want to address that 80% issue of decarbonisation, lots of these industries have this kind of problem. It's not just data centres. And you have to think about how we move from, you know, today's society, on the left-hand side of the graph, is looking at how today's construction for nuclear is done. Hinkley Point C, large, 15 billion started out project and is now circa 42 billion. Why? Because it's a huge construction project. It's really complex, really difficult to do. So how do you move the projects away? Oh, it's fine, we'll build more. We'll build 5, 10 of these. It'd be great. We can do it much cheaper. Yeah, Baraka did that. Great. Fantastic savings. But is it enough to compete? No, it's not enough to compete. You have to change the way in which we do that. So we have to move to a program build. But fundamentally, we have to move to a place where we can deploy the technologies much, much faster by doing a product build. What do I mean by product? Well, all the diesel generators that you have on nearly every site, in the UK alone, it's 10,000 diesel generators, right? Those diesel generators come out of a factory and they're ready to operate. You fill the fuel when you get to site, job's good, and you start producing the energy. How do we do that in nuclear? What do we have to do? And there's reports that kind of say, yeah, we can move the cost of nuclear down drastically. And if you look at those costs and what you kind of get to, you start to compete with today's price of gas. That's really interesting if we can move that way. So how do we transform that project that's really complex? Well, we take the parts, take them all to pieces, and we assemble them in modules. Great, we've got modules. Lots of SMRs are saying we'll have modules. That's great. But how do we do that in a factory environment, just like a car is done, so that you have a plant coming off the production line every, when I worked at Jaguar Land Rover, it was every 17 minutes a new car came off the line. Right? How do we do that in nuclear? What kind of things do we have to have in place? Do you want to just turn the volume up, if you can? So what we've done is we've looked at how we can repurpose old coal-fired power stations using this approach. We have a kit of parts that looks at the existing power plant and what can be reused and what can be upgraded or what needs to be replaced. We look at how those advanced heat sources, the heat boxes, effectively nuclear reactors, can be positioned, not one large reactor, but multiple reactors side by side, like Lego bits coming together to repower those coal-fired power stations. We've looked at how we can optimize the deployment of those. how we can get the configuration tools, the software to look at, well, if I do it at this site, this site, this site, there's 15 different sites, or 40 sites, or 100 sites, how we can optimize the schedule to deploy that technology. So we can look in detail about what the configuration is for an open architecture. So if you want to have a laptop, you have a USB port and you can plug it into a USB port. Everyone knows you need a USB port. It's almost the same you could do with nuclear. You can have the balancer plant where everyone knows if I can plug into that balancer plant, then I can put my reactor on it. But what kind of reactor would you have? You'd have smaller ones that can fit into that configuration architecture. But then by doing that, you can streamline what are the benefits to each region, each location, each site, and why is this the best way to deploy? What savings would you create? What kind of opportunities can you give to people with their workforces? How could you implement it with all the different industrial applications that are near it? What's the optimized approach for deploying nuclear technology? So as I mentioned, we use an open architecture approach, which you can combine together on any of the sites with the site configuration tools that help you to map the detail of those sites. We use AI and digital licensing, and that's a big statement to say we use AI. But what I really mean is we're working really close with Microsoft on developing artificial intelligence tool that allows us to do the site planning applications for any nuclear site. So right now what we can do is we can generate your environmental impact assessment, not within 3 to 6 months, within 3 minutes. If not faster, if I'm honest. But what we have to do is we have to train that AI. So we train it and we develop it. Microsoft developed the back-end side of it. And of course, it will use their Azure platform, which is where everything gets hosted. So you'll have services that come out of the back end. But it allows us to develop that licensing application much, much faster, which is what you need to be able to support new industries. So if you look at repowering using this approach, you could, yes, have coal-fired power stations with a standard module that fits into those stations, and you reuse a lot of the technology. But you could apply the exact same approach to shipyard and look at how you do fuel production platforms. Or you could look at FPSOs and how oil and gas industry could decarbonise. And I'm not just saying this with nice pretty pictures that we've drawn. These are from where we've worked with customers, oil and gas companies, to utilise nuclear. That kind of sounds strange to me to always say oil and gas companies, but we're looking at not just small-scale production unit with a small little reactor that does a small power. It's about being able to lump those reactors all together. And by doing that, you can scale to any size. In fact, this is a 10-gigawatt hydrogen gigafactory that we were looking at, in particular using a light water reactor technology. It doesn't have to, but this is the one that they wanted to look at. And you can start to see maybe there is a different way to get energy demand to sites. Maybe there is a different way to get that price of energy that I talked about with a bit of an analysis to get the costs right down to be competitive. Maybe there's a way that we can start to use that strategy, that analysis, to underpin how we get energy and the capital cost of energy from $6,000 per kilowatt down to $2,000 per kilowatt. Because if you can do that, nuclear becomes really, really attractive to every energy user. So what we're trying to do with the regulators is to work with them to define, okay, we're going to regulate really fast within 3 minutes an EIA. How are you going to regulate on the other side of it? So they've said, yeah, that's a really good point. We actually need to develop our own AI configuration as well. So again, there's two sides of the coin. It's all great, us saying we can do this from one side, but the regulators and the industry behind making these things happen, that also needs to move forward too. So as we go through, we start to hit those new industries, and we have to work at an industrial level, and it's not just one area for nuclear. Now what we're finding is I'm no longer presenting to a nuclear audience. I'm now presenting to a lot of people that have never worked on nuclear. Data centers are calling me in, oil companies are calling me in to talk through how do we convert our cruise ship into a nuclear-powered cruise ship? How do I convert our drilling rig to a nuclear-powered drilling rig? There's a lot of challenge, a lot of change, but the underpinning analysis that we do, working with lots of people that you'll have heard of. In fact, you can see some of those names on here. We start to really, really get into the detail of how would you do it for nuclear and what kind of things would you need to do. And we've got a lot of partners that work with us. So those were our customers. These are our partners that help us develop in TerraPraxis. And Project Phoenix, the video that you saw is us looking at the Ukrainian coal fleet on behalf of the US government. So thank you for listening, and if you've got any questions, feel free to ask.
Thank you very much. Thank you very much. Thank you very much, Dr. Dury. Dr. Dury gave us a full outlook, I think, of the nuclear market, potential challenges, as well as some projections. Professor Pourica will give us now the status related to Romania and the region. Professor Pourica is online. Can you hear us? Hello. Professor Pourica? If there's a bad connection, we can go on with Mr. Hionis and then proceed.
Can you hear me now?
Yes. Okay. Please, go on. We can hear you, Professor. Yes.
Okay, I'm starting my presentation. It's about new SMR, small modular reactors in the Romanian system. Romania first, you have that has a long history of nuclear energy. And the idea is that although nuclear has saturated up till and a little after the Fukushima accident in 2011, now there's a new start with everybody doing various type of reactors. Romania has started back in 67, 68 to cooperate with Canada, with the approval of the US Congress, to transfer natural uranium fuel CANDU technology to a country that at the time was a member of the Warsaw Pact. Glenn Seaborg and Romanian Horia Hulubei were discussing and agreeing on transfer of technology. And now Romania has a full fuel cycle, actually starting with uranium ore, with still sizable reserve of uranium, although we are buying outside the country just to keep our uranium in reserve. The fuel ore is processed into CANDU fuel. CANDU fuel that goes into the power 2 unit, 700 megawatts each in operation, and then the waste fuel is disposed. This is a picture of Cernavodă nuclear power plant. The first 2 units are in operation. You don't see the unit 1. It's, wait a moment. It's here. And it's units 3 and 4 that are now under financing to be finalized. they are about 30–35% ready. Let me talk about the nuclear. Just a minute, excuse me, just a minute. Hello? Alo? Da, vă aud. Spuneți. Alo?
Am o întrebare. Vă auziți, domnul profesor?
Da, vă aud, vă aud. Alo? Sorry, it was the Minister of Energy on the phone, so I had to make a small pause. The idea is that Units 3 and 4 are reducing and are contributing to the security of the operation of the system, of the whole system. And it's a very interesting thing that Romania is now doing first research on a type of small modular reactor and developing the construction of another type that was the first type of reactor certified by a Nuclear Regulatory Commission in the States. Let me talk a little about the idea of developing capabilities for modeling the energy. We are using IAEA message model. You have here on potential cumulative uranium consumption, various penetrations of energy in various scenarios. Let me talk about old to new technologies. This is the control room of the research reactor that was operational in Romania in October 1957. We were, I don't know, the sixth country with a nuclear reactor in the world. A long road has been and see the control room of Chernovoda nuclear power plant, as I told you, 2 units of 700 megawatts. Slight difference from the first. This is the reactor, the research reactor under decommissioning, is decommissioned now. Just to make a little history, it was called power reactors in small packages back in '68. And the United States had got a full program of all sorts of such reactors that were either put in transport by plane, for example, put it in some military bases, or in the McMurdo Antarctica base, also put on a ship that was on a boat that was sent to various locations to supply power and even heat. Nowadays we have evolved a lot. There's a frenzy of small modular reactor design. You have some examples, and obviously the Russians have put also some reactors on a barge, and they are sending it on the rivers in Siberia to supply power and heat to the cities there. Basically, there are thermal and fast breeder reactors, and you have a selection step here. I don't want to get into these details. This is NuScale. I told you we are making a power plant with 6 nuclear reactors like that, small modular reactors. That's why they are called modular. And obviously, the thing is that we are in a position now to make the engineering procurement and construction study to finalize the first stage of of this power plant. It is financed. Finally, I want to mention that together with Ansaldo and Enea in Italy, we are developing an advanced lead fast reactor European demonstration, ALFRED. You know, these acronyms are sounding nicely sometimes. The idea and the advantage of developing such a model of small modular reactor, it's about 300 megawatts thermal. That means 100, 120 megawatts power, electric, is that fast breed reactors are able to use fuel that is made out of waste fuel from Candu, and just mentioning that uranium-238 in waste fuel is actually turning into plutonium-239 that is fissionable and used in fast breeder reactors like this one. This is actually reducing the amount of fuel deposit. The last thing I wanted to put is that take care in nuclear, as in energy nowadays, there is a fifth night of the apocalypse called misinformation that may lead from evolution, and this is Constantin Brâncuș, Column of Infinity, in a nice picture. Evolution to the end. And this is the end of my presentation. Thank you so much.
Thank you.
Thank you so much, Professor Pourica. The first two speakers gave us their approach of challenges and opportunities. Now,
I have to, I will send my presentation and be ready for whatever questions to reply by mail.
yes, sure.
To bring such interesting topics on energy. All the best.
Thank you. Sure. Thank you, Professor. Now, Mr. Hionis will give us the market opportunities as well as the recent developments and the situation in Greece. Right. Please, the floor is yours.
Thank you very much, and especially thank you to all these courageous people in the audience that decided to stay until so late and hear the last part about nuclear energy. I truly believe that we will face a moment that nuclear energy will be the first panel of such conferences and not at the very end. So, in contrary to what the two previous presenters said, Greece is a non-nuclear country, therefore please allow me to make one step back, because I'm pretty sure that your understanding about nuclear is not so well established as in the UK or in Romania. I have the pleasure to work in the nuclear industry in my day job during the last 15 years in Switzerland, and today I'm here by representing my new company, Athlos Energy, which is the first nuclear company, Greek company in the nuclear industry. But before talking about my activities in Athlos Energy, just allow me to give an overview about why we are talking about nuclear. So, nuclear right now is a reliable, stable, and proven technology. Here we can summarize very short for which reasons so many countries in the world focus on nuclear. Nuclear operates 24 hours per day, independently if it is sunny, if it is windy, if we have battery or not. nuclear power gives you nuclear security and independence. In addition, it is a green source of energy. We do not produce CO2 or other greenhouse gases. Even the European Union decided 2 years ago to include nuclear as a sustainable solution, which means that companies can invest by getting credit of tax reductions by investing in nuclear energy. We should not forget that nuclear is a technology that allows you to make geopolitical connections for decades with strong partners. Just see what is happening right now next to us in Turkey. Turkey is constructing maybe the largest nuclear power plant in Europe at Akuyu, which is just above Cyprus, under the agreement with Rosatom, the Russian company, and for the next many decades they will have strong geopolitical relationships with them. In Bulgaria, the government decided to sign contracts with Westinghouse, which is an American company, in order to continue a long decades collaboration, very strategic for their country. When a country invests on nuclear, there are very big profits for the industry, but also for the government through taxes for not 10 or 20 years, but for 60 plus years. Right now, the nuclear power plants operate for 60 years, but they have received approval from the regulatory bodies in the US and in the UK to operate for 70 and 80 years. And last but not least, the job security, but also the local economy and the community are significantly improved in the areas where nuclear power plants are constructed. Here we can see just a summary of around 440 nuclear reactors, big nuclear reactors operating throughout the world. On the right, you can see what is the situation in Europe. Unfortunately, Greece is a non-nuclear country. However, right now, our neighbors in Turkey, in Egypt, in Italy, but even in Serbia are very actively discussing about entering the nuclear business. Some numbers on the top. In 2023, the nuclear reactors worldwide produced 10% of the electricity production. So nuclear is not something small. Nuclear is here. It's proven and very well established. However, there is a new kid in the town, and this kid is called Small Modular Reactor, abbreviated as SMR, as Mikhail previously said. So the idea of the nuclear reactors pretty much didn't start now. It's around for a couple of decades. The SMR vendors, the companies who are constructing SMR, small modular reactors, developed their ideas in order to give answer to the big bottlenecks and challenges that we have in the nuclear industry. Many people say that nuclear is expensive, it needs a lot of time to be constructed, it's not safe. However, the SMRs are designed in order to be economic, safer, and to be employed much, much faster. Here we can see that we have a big nuclear reactor, the traditional nuclear reactors that we have throughout the world, which have typically an installed capacity of 1 gigawatt, 1,000 megawatts. But the small modular reactors go down to typically 300 megawatts. They can be constructed at a reduced cost, or they are said to be constructed at a reduced cost. They can be constructed at a reduced time. They have even safer features. And last but not least, as it was said before, they are meant in order to be constructed as modules, which means that if you want, for example, to go to 1.2 gigawatt, you can build 4 of these modules of 300 megawatts, and then if you construct and operate the first module, you can earn money and you can start investing this money on the second module and then on the third and the fourth. So, based on the report that you can see, there are different number of designs. I get here the numbers from the International Atomic Energy Agency, which is the body under the United Nations in Vienna. And there are 68 established designs throughout the world. typically is stated that are designed by 18 countries. And here I want to emphasize that the majority of these small modular reactors are pretty much scaled down conventional reactors. Pretty much the developers wanted to leverage the experience of the existing operating reactors of 1 gigawatt and make them smaller. And by having also much improved safety features. These reactors are in most cases in a design phase, but they are currently constructed in countries like Canada, Argentina and China. And we believe that even in Europe, by 2030, we will see the very first construction of these conventional small modular reactors. In addition, there are many designs in the US, in Korea, in China, and in Russia, focusing on the nuclear maritime. We had the opportunity before to hear that the maritime sector has to be decarbonized by 2050. And with the conventional alternative fuels like methane, LNG, etc., this net zero by 2050, it's common truth that it will never be established. So the maritime sector says that we need another solution. And one solution is nuclear propulsion reactors. The first nuclear maritime reactor is already operating since 2020 in Russia. A professor from Romania previously said that. It's called Academic Lomonosov. Pretty much it is used in order to provide electricity to isolated locations in Siberia. So whatever region in Siberia needs electricity, this nuclear ship goes to the port and provides electricity. Furthermore, on the top right, there are many small modular reactors which are focusing on high temperature steam production, more than 750 degrees C. That clearly indicates that we can use these designs for industrial application, even in Greece, for example, for aluminium production. And last but not least, on the bottom right, we have many designs that are focusing on advanced concepts by using different kind of fuel, not the conventional uranium, but thorium, for example, or molten salts, and different types of coolants, which can give you better efficiency and better opportunities on application. So, here I just highlight some key recent developments on innovation. And one of that, as Mikhail before mentioned, is the fabrication on the factory. So pretty much instead of building a huge nuclear reactor on the land and having thousands of people working there, the idea is that you pre-manufacture these components on the factory, let's say whatever is that in the UK, in France, and you put it in a cargo and you just transport it to the place that you want to install it. That pretty much decreases significantly the cost, so the capex, but also the construction time. Then there is a lot of discussion that you cannot use nuclear power in order to do load follow. We know that, and we heard that today, that we have sun, we have wind, they are very stochastic, but how can you use this kind of base load applications in order to follow their stochasticity? And for that reason, many power plants like in TerraPower from Bill Gates, they have the capability, or they are designed to have the capability to ramp down to 10% per minute, or for example, to go from 100% power to 20% power within 30 minutes. And of course, when you use modules, you can simply remove one module from the grid in order to follow the load. Furthermore, all these designs utilize passive safety systems. In the nuclear industry, we use this term very often. What passive safety system means, it's pretty much that you don't have pumps, you don't depend on external electricity, pretty much you depend on gravitational forces, and the human intervention is so minimal that pretty much makes your reactor much, much safer, even safer than what it is today. And last, as I said before, there are many designs like the Bikala design in Sweden, which use alternative fuels. It creates a new supply chain in order to explore much bigger markets. Here, it's pretty much a summary of what you can use with nuclear energy. People think that it's just for power generation on the right. However, you can use nuclear energy in the entire spectrum of the steam temperature in order to produce hydrogen, in order to produce fuel cells. This is something that typically people cannot capture, but it's one of the applications that nuclear energy promises to solve. And that pretty much brought me, together with my partner, a couple of years ago, to the idea of forming Athlos Energy. So we understood that Greece has very ambitious plans. By 2040, already by 2040, we want to be pretty much fully depending on sun and solar. You very well know the National Plan for Energy and Climate, Εθνικό Σχέδιο για την Ενέργεια και το Κλίμα, which we find that without an established base load, it cannot be achieved. Therefore, we want to bring nuclear energy into Greece, and most important, to create a fundamentally new market. Both me and Stathis, my partner, graduate here at the National Technical University of Athens as mechanical engineers. We wanted to follow our dream about nuclear energy, and we moved 15 years ago to Switzerland, where we studied, we did our master and doctoral studies at ETH in Zurich. And we are working since 2018 in the nuclear industry of Switzerland by having a very well-established position in the international nuclear industry. With Athlos Energy, we have a very clear mission. We want to provide a realistic and pragmatic alternative to the Greek state in order to achieve the ambitious goals for the energy and climate. And our vision, even if you read that and you think that it's crazy, it's very clear. We want to develop and execute the very first nuclear program in Greece. We are not the first ones who want to do something like that. In other countries like Estonia, 5 years ago, 3 crazy people like me and Stathis had the same idea. A country which was depending fully on Russia from gas and crude oil. And today, just 5 years after their first idea, nuclear is part of their energy plan. And as we heard before, there are so many opportunities for Greece in the nuclear sector. First of all, most of you heard at the end of March that the Greek government decided to make huge investments on the Western Macedonia in order to bring the coal plants, the lignite plants, to a new era. We want to invest on PV, we want to invest on natural gas. However, that will bring us to 2035 to 2040. And what do we do afterwards? One of the solutions is to transform the lignite and natural gas plants to nuclear. This is something that has happened in many other countries, like in the US. Of course, we can use nuclear power plants in order to electrify isolated areas like islands. We've heard, I don't know how many data centers we want to construct in Greece, I think so, 16. We've heard how big are the electricity demands, and the question is, how are we going to electrify these data centers? As we heard before, Amazon, Google, Meta are investing a lot of billions on nuclear in order to electrify data centers. Greece is one of the biggest players in the maritime sector. As we said before, they have very clear net zero goals by 2050, and there is a lot of discussion to move towards nuclear propulsion. Right now, together with my partner, we have established very close communications with all the big industrial players into Greece, and all of them understand the need of nuclear. We have to go there. But with the help of Atlas, we can prepare the background in order for everyone to enter in this nuclear business. And last but not least, pink hydrogen. Pink is my favorite color. Is the hydrogen that you produce by using nuclear. I don't really like that in EU we say that green hydrogen is only if you produce it with renewables, because when you produce hydrogen with nuclear, this is also green. However, if we want to focus on hydrogen and district heating, nuclear can be a great solution here, and this has been already demonstrated, for example, in the US with the pilot proof of concept project. So I just complete here. We are very new, we are since September, but we believe that we have already established our position in Greece as the reference point for nuclear energy. We have a very clear path to go towards into development and implementation of the first nuclear project in Greece. We are searching for partners which are purpose-driven, and we are very open to discuss with anyone who has similar ideas. Thank you very much.
Thank you, Dionysis. So in order to see the market taking off, Dr. Drury, in order to see the market taking off after 2035 and accelerating after 2040, as you mentioned in your earlier, right? We need successful demonstration projects, right? I mean, favorably, excuse me, and favorable economics for these plants. Will we see that, or will we instead see the initial projects not be so successful, including in terms of cost, of course?
Yeah, I think it very much depends on every technology, and every vendor has a very different approach at the moment. So typically, most of the vendors that are kind of utilizing existing pathways for validating their reactors are light water reactor technologies, because predominantly that's what we've got around the world. It's the most common reactor type. Mm-hmm. Yes, we have CANDU reactors, which you saw in Romania. And yes, we actually have a molten salt reactor operating in China now. And yes, we had sodium-cooled reactors in the past, and molten salt in the past, and lead-cooled in the past as well. They were all generating in the 50s. Mm-hmm. But the problem is that the data that's available to validate those Gen 4 reactors, it's not available in a way, in a format that you can justify to the regulators today. So what they have to do is redo the tests that validate against the software and the codes that say this will work, that you're using for the regulator today. So you need, for those Generation 4 reactors, you need to do the testing to validate for the regulators. It doesn't mean it doesn't work, it just means that there's no referenceable data that you can utilize, because things like the molten salt reactor experiment that was done in the USA, it was done at a time when the codes weren't available. So now we use things like Serpent, EEE, Scale 4.2, all the same kind of things for doing transient analysis. And we can't really use it because the thermohydraulic to reactor physics coupling doesn't exist.
Actually, there's a new mission here for regulatory drivers, right? For the regulatory bodies in Europe.
Yeah.
Yeah, which is, I mean, I wonder, the numerous regulatory bodies in Europe could limit the overall internal market. Are you worried about that?
No, I think
there's so many regulatory bodies.
At the moment there is a level of cooperation between the different reactor vendors between the different regulators. So CNSC, NRC, the ONR in the UK as examples are all working together to I would say harmonise the regulation. It's not quite, it's to share the information that allows them to use that information for faster vendor approvals. Mm-hmm. So it's slightly different to harmonisation, but it's definitely looking to how do they fast track the development of their regulatory pathways to shorten them. So UK as an example had a generic design assessment process that was 5 years, and they've magically reduced it to 4 years. That's amazing. I don't think it is. But the challenge really is, can we get it down to 6 months? And how do you get the tools in place to do that kind of regulation? That means changing the way and the approach that you take for regulation, removing lots of elements from regulatory path for license applications that aren't really necessary and can be done elsewhere in advance of any project. And that's the whole purpose of things like manufacturing license applications, which we already do in nuclear. So it's not a new process, it's just not really been applied to new reactors. Because, to be honest, we've always used light water reactors as the next reactor. So why bother? You don't need to. The evidence is already there, but now you're having to generate evidence. Actually, you need tests. So Switzerland, as an example, there's a molten salt reactor program that's being developed. Alfred, you saw in Romania. There's another one in France, which is with Nucleo, that they're doing, which is a lead-cooled reactor. And there's also a molten chloride.
Estonia and Poland are also active, aren't they?
Yeah, but more on looking at deployment scenarios. So what you're finding is a lot of countries are taking the light water reactor route because it's easier to deploy, because the regulatory pathway is there. Maritime is another example where the regulation globally and internationally actually is already written in maritime law for light water reactors, but it's not written for molten salt or lead-cooled or sodium-cooled, albeit that lead-cooled reactors are actually in operation in maritime, just not in civil nuclear applications.
Okay. Thank you. Professor Purica, is he available or not? Okay, okay. So then, sure. No, it's a more a question focused on the Greek case now for you. I mean, I was wondering, are we fully aware in Greece that two neighbor countries, Egypt and Turkey, are building enormous big nuclear plants on the Mediterranean? I mean, could this news that the first reactors turning on in Turkey and Egypt, could that be a shocking moment, a shock development for Greece and Greek society, and could that lead to a national conversation on the need for nuclear, or not? Well, what's your take?
Yes, clearly yes. I mean, if you ask the public, most probably they are not aware that Turkey is constructing, and also Egypt, their nuclear power plants. If we go back in 2004, when we had the Olympic Games, you have to know that without the support of Kozloduy in Bulgaria, the nuclear power plant, it would be impossible to run the Olympic Games, because suddenly in 3 months we had such great electricity needs, and we were importing nuclear from Kozloduy. I think so, coming to your question, that the turning point will be beginning of 2026, where President Erdogan last week announced that the first of the 4 units in Akuyu in Turkey, a nuclear power plant, will be connected to the grid. And by 2029, all the other 3 units will be there. I have to highlight that Turkey doesn't stop there. Already they have made a request of bid for the second site in Sinop at the north of Black Sea for 4 more units, and they're already discussing for the 3rd site to the border of Greece in Thrace. So Turkey will become a huge nuclear player, and I am 100% convinced that that will be a shock for the geopolitical situation in Greece.
Another one for you, Dionysis. Greek society is against nuclear energy. I mean, according to the Eurobarometer, to the last one, 55%, if I remember well, is against, 40% 45% is in favor. How can Greek society be convinced? And moreover, does Athlos plan to conduct research on the matter? Yeah.
If we go back in 2018, when the Greek Energy Commission, so the regulatory of Greece, conducted a survey, 2018, 75% of the people were against. 25% of the people were pro-nuclear. Right now, it is 55%
So
against.
things are changing.
Things are changing because people understand that all the promises on investing on renewables, which would result to lower electricity prices, didn't materialize, right? So the public perception is very important. Without public perception, it's one of the three pillars, together with industrial support and the governmental support, you cannot proceed. And something that we try to do since September, and also today we do that, we try to communicate with very clear words to the Greek public what nuclear means. Nuclear is not, I think, so as you said, AI is not panacea, right? Nuclear is not panacea. Nuclear will not solve everything. Nuclear has advantages. Nuclear has challenges. What we try to do is to explain to the people which are the advantages, which are the challenges, and that will help the people to understand.
Dr. Drury, could we see a nuclear hub in the Mediterranean? Is it realistic or not?
Of course it's realistic. Yeah, I don't see why it couldn't be. I think you're right, though, on public perception is your biggest obstacle to overcome. But when energy is turned off and you don't have energy, then you're going to have to find a solution. And if we start doing that planning now and putting the bricks in place and the processes, then you can be ready to install that new form of energy. I think we ran the same public perception in the UK. Now, we're a little bit more pro-nuclear because we've already got it. But we looked at all the sites that don't have nuclear energy. And we talked to those. So I was UK government at the time. And we talked to 3 non-nuclear communities. We talked to 3 non-nuclear communities. And those communities at first they weren't very supportive. But when we went through what nuclear does nowadays, how it does it, how it applies its approach to the projects, and how you support those industries, and how those industries then grow the communities, then you start to see, oh, actually, this is quite good. Why are we always worried about the waste when the total life in the current reactors, which only use 95% of the fuel, 5% of the fuel, the current waste is a Coca-Cola can size of waste for you for your entire life. When you look at some of these new technologies, and they then use 98% of the fuel, your waste is like a little marble of waste, and that's it. When you say safety, it's like, we are the most safe industry in the world for energy production, yet we always talk about safety. You jump on a plane, what's the first thing the guys say to you? Oh, it's safe. You know,
Yeah, sure, but
I think the way in which we communicate as an industry has never really helped to kind of go through why is this okay to deploy. And I think that public perception is really important to provide the education so that people make informed decisions.
it's also that UK has a nuclear story and Greece doesn't. That's what that was my point. We can also take questions, please, sir.
For Michael Drury and another one for Dionys Sionis. The first question is about hydrogen and nuclear. You showed a very spectacular schematic with 20 or 10 gigawatts and then a factory type industrial. And I cannot comprehend the relationship between nuclear and hydrogen. What does it actually happen? And the other question to Mr. Sionis is, you mentioned that Latvia in 5 years has gone nuclear. What does this mean? That it has actually built a nuclear plant, or it's getting electricity from a nuclear plant which is nearby, or, you know? Please clarify.
Thanks. So for nuclear and hydrogen, ultimately for any hydrogen production, you need energy. There are loads of different processes, and it was presented earlier, those different processes. So fundamentally, you either need electricity or you need a thermochemical process. Okay, so there's two kind of main ways of doing that. Nuclear could provide both of those ways, either by direct heat supply from some of the higher temperature type reactors, or from the electricity supply from all of those reactors, because they can all produce steam and then ultimately the energy. So nuclear can provide that, but why would you go nuclear? Why not just use free wind and solar? Well, actually, if you want to get the cost of that commodity down low enough, then it's about your capacity factor and how you can maintain your operation of hydrogen production for the life of that hydrogen plant. So really, it's about keeping that hydrogen production in process all the time. How do you do that? How can you sustain that? Nuclear allows you to do that because fundamentally it wants to stay on all the time, right? That's what you'd like to do. But you also have the ability with some of these reactors now to load follow. So you can use and switch if you did want to have a downtime in your hydrogen production plant to do that. But fundamentally, it's about capacity factor.
To your question, it's not Latvia, it's Estonia. So actually they plan to construct 2 units of General Electric. The design is BWRX 300. By 2030, they want to start the construction, and by 2034, they want to have the 2 power plants into the grid. So they have already selected the technology. This is General Electric. They have already selected the site, and they have already selected the main contractor, which will be Samsung.
Right. Dr. Drury, you mentioned earlier that there are more than... excuse me? Oh, another one. Please, go on.
Hi. We're talking about general nuclear power in general, but for Greece, we cannot compare Greece with either Turkey or Egypt. You know, there are much bigger populations. There's industry there. So the model, I say, you know, I mean, we have established Public Power Corporation has the big units that have been decommissioned, but they have not spoken about this at all. If I, correct me if I'm wrong, I haven't seen any of this stuff. So what is a realistic scenario for Greece per se? And I know that the Development Finance Corporation, the USA, finance group, government or semi-government, actually quasi-government, they finance. This is one of their targets, to finance, American U.S. nuclear technology, and that's I think in Estonia. That's where the financing, some of it comes from, if I remember correctly. But the model for Greece is not the same as it is for the UK, for example, right? It's totally different. You must have industry to really use it, and the cost-benefit analysis. Really, that's really one point, the cost-benefit analysis, and understand all the clean stuff. And at the end of the day, will we pay less for energy, industrial and commercial, and also private, for our homes? Because that's how people will understand it. All the other technical stuff is great for panels and all, and I'm with you guys, and thank you. It's just how we get the message across, and how it affects us in our daily lives.
I think you're totally right. The market between the UK and Greece is completely different. I totally agree with that. We talk to a lot of end users globally, and actually, the question that always comes up is that cost-benefit analysis. Tell me why it's right to go to nuclear for us as a business or as an industry. And fundamentally, it always comes down to cost in one way, shape or form, whether that be costs and improvement to life because of jobs and things like that, or fundamentally the pure cost of energy. But to achieve that low cost of energy, then you have to change the way in which we deploy nuclear. And that's how it becomes attractive to countries like Greece that may be looking for that lower cost and that lower band and that lower threshold, and not just about decarbonisation? Because some countries are not looking at decarbonisation. It's purely on the cost of energy.
May I add on that? Fully agree. I mean, Turkey is planning to install 20 gigawatt of nuclear. This is, of course, no-brainer. It's not relevant for Greece. But in Greece, every hour of the day, any day, we use around 1.2 to 1.5 gigawatt from coal and natural gas. Every hour.
Every hour, you mean?
Every hour of the day.
1.5.
1.5
right now.
Right now it's 1.5. Even in middle of August, if you check the data from AVMIE, it's gas and lignite. So the idea is that with nuclear, you don't have to put 20 gigawatt. You can start with 300 megawatts. You can start with 1 gigawatt, but you have to do the first step. And here on the price, it's a very correct question. In order to answer that, you have to do very, very technical, techno-economical analysis. However, Professor Biskas, Padelis Biskas from the University of Thessaloniki, who talked earlier this morning, he published a paper, I think so, it was in a conference of IENE, or not, I think so, in autumn last year, where he analyzed that the introduction of nuclear into the Greek electricity mix can reduce the electricity price by 25%. This is, of course, just one analysis, but it shows the trend. If you want to have a very clear understanding, you have to do very dedicated analysis on that perspective.
Dionysius, because I remember Professor Biskas' analysis, the cost could be downside between 3% and 25%.
The best case scenario was 25%.
Yes, the best case scenario was 25%. The worst case scenario was
3%.
3 to 4%.
Yeah.
Accordingly, the cost impact for consumers could be between €3 and €25 per megawatt hour, according to that study. And of course, Professor Biskas emphasized in that study that the benefits only exist if the country is limited to installing about 600 to 700 megawatts of nuclear plants, of SMRs, right. So this comes to a question, we were discussing that earlier, how many SMRs, a country such as Greece, with a consumption not more than 50 terawatt hours per year, right? 52 terawatt hours per year, more or less. Such a country, how many SMRs may need in order to achieve a nuclear share of, I don't know, 20% of the total mix, of the total mix?
Well, I think for answering the question, it's a really difficult question because each SMR is a different vendor, will be a different size. So your typical kind of SMR, which is the IAEA kind of guideline, is a 300 megawatt is your threshold for an SMR, right? Rolls-Royce's reactor is 470 megawatt. That's above the threshold. Copenhagen Atomic's reactor, which is one reactor, is in a 40-foot shipping container. That's 42 megawatts electric. So when you ask the question of how many, it's like, well, how many of what do you want? Which one do you want? Which technology do you want?
How many of these 300 megawatt type?
So you've got roughly 25 gigawatt of capacity. 25 gigawatt of capacity, if I look at the energy that's being used today. When you look at that, that's equivalent, if you had 300 megawatts, that's 0.3 of a gigawatt of a reactor, that's 83 reactors if you wanted to completely change and cover everything. So if you put that into perspective and you wanted 20%, that's 16 reactors, if you wanted to go down that route. But it very much depends on what you need and actually what are you trying to get out of installing for Greece. Is it about distribution network and reducing the reliance on the network and shoring up? Is it about actually you don't want to have that waste and you want to have the right kind of reactors that get rid of the waste? Is it that you want the heat for industrial applications, or is it that you want the electricity to support that aluminium production process? What is it that you want it for? The benefit that you have of the reactors today and the marketplace today is that there are a plethora of different reactors that address very different things. You know, like if you want one that you can throw something at it and it won't go everywhere, a high temperature gas reactor with its TRISO fuel is very helpful for that because the fuel is protected. So there's lots of different things that you need to...
You mentioned earlier that there are more than 90, if I remember well, there are more than 90 concepts proposed regarding the SMR development.
In development at the moment, yes, there's more than 90. And they share across...
This variety make it difficult for end users to identify the best solution, right?
Yeah, it makes it really different. So we talk to a lot of different users, and they're saying, which reactor should we use, Mike? And we go, well, okay, well, what do you want it for? And then we go through the assessment, and it goes back to the gentleman's point of, you know, what's the techno-economic assessment for my use case scenario? And that's where it comes in important to understand what are you trying to do and for what reason. And then you can start to say, okay, I want a reactor tomorrow. Okay, tomorrow it's got to be a light water reactor because it's licensed, you can refer back to stuff, it's quick and easy.
No, yes. Last one for you, Dionysis. The question is clear. I mean, for what reason do we need? And I remember Premier Mitsotakis' older statements that Greece is closely following all the developments regarding the SMRs. Where are we now?
I don't know what they are doing in the government and how closely they are following the technology. From my takeaway is that for Greek government right now, nuclear is not a priority, but they understand the need, as Prime Minister mentioned. But to my knowledge, there is no active group following the different designs. But if I use my daily work on the nuclear industry, we are discussing that there are so many designs, 90, but this is not sustainable. Eventually, we all very well know that in the next 5 to 10 years, we will convert to 3 or 4 designs, and these will be the ones which will be employed. So we don't have to focus on everything.
Okay, our time is up. We have provided some answers. I tried to make a deep dive on the nuclear topics. I thank you all, and I thank you also for your watching.